Okay, so let's wait a minute. So what we are doing is basically we are doing some row operations and we are finally telling something about the columns. This is what we are doing, right? What I mean to say is that in Gaussian elimination, we are doing some row operations, which means we have some rows and then we are saying that, okay, what if we subtract this row from that row and finally like whatever, right? This row from that row. Some elementary row operations we are doing in the rows. And then ultimately we are saying that, okay, these are, let's suppose I do something. Okay, let's suppose I do something and I get zeros here. Okay, the last row is zeros. Then I say, and these rows, let's suppose this is having some non-zero, some non-zero like that. So suppose these are the three, let's suppose these are the three non-zeros. Then I say that number of linearly independent rows are 3, and hence number of linearly independent columns are also 3. You're getting my point? What I'm trying to convey is that we are doing some row operations, and then after the row operations we are saying that, see, number of linearly independent columns are equal to also 3, which means not only we are talking about the rows, which means not only we are saying that number of linearly independent rows are 3, we are saying number of linearly independent rows are equal to number of linearly independent columns, which are also 3. Basically, we are doing some row operation, and that is fine that we are saying number of linearly independent rows, because ultimately we are subtracting out some common factors and finally making as much as zeros as possible, right? This is what Gaussian elimination do, that okay, here all zeros and then all zeros and like that, right? That's what the Gaussian elimination do. So number of linearly independent rows, that's okay, like we can say something like this. But why we are able to claim that number of linearly independent columns and number of linearly independent rows are actually equal? That is my question. That's what I have said. Wait a minute. Everything is over, but just a minute. We are doing some row operations and telling about the independent columns, how it is possible. Let's just see. So for that, I want to give you one example. Okay. So suppose that you have one matrix. In that matrix, let's suppose there is there are some numbers. Maybe let me take 1, 2, 3, and then this is some number, maybe 2, 4, or maybe 2, 3, 4, something like that. And then let's suppose this column is linearly independent on these two columns, and which is, let's suppose, 3, 5 and 7. Okay, suppose this is the case. So what I'm saying here is that this column is linearly independent on these two columns, and the exact relation, I can also write the exact relation, is C1 plus C2. See, if C3 is this column, then exact relation is C1 plus C2. This is the exact relation. Now, what we want to do, we want to, like, any random elementary or row operation I want to do. Anything of your choice. Okay, can I do R1? Can we replace by R1 plus R2? Actually, anything of your choice you can do. Okay, I just want to convey one thing, and that will be conveyed by anything of your choice of this elementary row operation. So suppose this is 1, 2, you are replacing R1, right, by R1 plus R2. Then it will be 3, it will be 5, it will be 8. It is 2, 3, 5, 3, 4, 7. Right? You are replacing this row by these two rows, the summation of these two rows. Then you got this row. That's perfectly fine. Now earlier, if you remember, I said that, okay, C3, the relation between these two columns, these three columns, is basically this column is linearly dependent on these two columns, and this is the exact relation, C3 equal to C1 plus C2, right? Now, let's just check whether the same relation holds here or not, which means, is this column is still C1 plus C2, which means these two columns, just check it, 3 plus 5, 8, this is 5, this is 7. Yes, 8, 5, 7. So which means that this is still holding the same relationship. You do one more elementary row operation, or anything, any number of elementary row operation. Maybe you do R3 minus R2, anything. Okay. Then if you do R3 minus R2, you will be getting, this is 3, 5, 8. We are replacing R2, right? So by R3 minus R2. So 1, 1, 2. This will be 1, 1, 2. This is 3, 4, 7. Now just check whether these two summation is giving you this or not. 8, 2 and 7, right? So yes, it is giving you this, which means that the linear dependency among column remains same, which means whatever the linear dependency here you have is the same linear dependency here you have is the same linear dependency here also you have, isn't it? So we will study one form called row reduced form. There I will tell you one more thing, but here just observe the linear dependency which is same, right? That's very nice. Very, I mean, ultimately is ultimate nice thing that the linear dependency remains same. So here I'm saying if C3 equal to C1 plus C2, here also C3 equal to C1 plus C2, here also C3 equal to C1 plus C2, right? Like if I just try to give you one example, let's suppose that I say this is 1, 2, 3, this is maybe 4, 5, 6, something like that. And here, let's suppose I say this is 6, this is 9, this is 12, right? Suppose, which means this is, I think C3 is 2C1 plus C2. Let's just check if it is 2C1 plus C2. Yeah, the way I made it, yeah, 2C1 plus C2. Now suppose like just a hypothetical question, and we can actually frame such question in the weekly quiz also. Suppose they say that because of unknown elementary row operations, you get something like this. Okay, you got something like this. Because of unknown elementary row operations, let's suppose I'm writing some random numbers. I'm not sure using the elementary row operation it will be obtained or not, but some random numbers I'm writing. Okay, so don't mind it. So let's suppose I'm writing 2, 3, 5 and 4, 6, 7, and then here I'm writing ABC. Okay, so what they're saying, the question is that because of some unknown elementary row operations, you got this matrix. Okay, which means I'm saying this is 2, 3, 5, 4, 6, 7 and ABC. And because how I got it? Because of some unknown elementary row operations, right? Now they're asking you, what is the value of A? What is the value of B? What is the value of C? So just try to visualize it, like how you can do it. Will you see, one way is that you just convert this matrix to this matrix and just see that what is the best way to convert this matrix to this matrix such that you get 2 here, 4 here, something like that, right? Another way is that you know that okay, this is the linear dependency between columns here, and the same linear dependency must hold here also, which means A must be equal to 2 into this plus this, 4 plus 4, that is 8. B must be equal to 2 into this, 6 plus this, 6, this is 12. C must be equal to 10 plus 7, which is 17, isn't it? So that's how you can solve this question very easily. So what I mean to say, that if you have any linear dependency, whatever it is, that get preserved using elementary row operation. Okay, see, there is something called as row space, there is something called as column space. So I'm just telling you one line, and maybe in future in the masters, so that you don't get confused, so I have to take care of all the things. Using elementary row operations, the row space get preserved, but column space doesn't get preserved. Okay, there is something called column space that doesn't get preserved using elementary row operations, but row space get preserved. But the thing that I'm talking about is not column space, I'm talking about the linear dependency of the columns. Okay, so you just skip whatever I said in just previous 15 seconds, because I just put it as a disclaimer in case if you go for masters, there you should not get confused that okay, what is happening. Okay, because sir said like it will get column space will get preserved, because I never said that column space will get preserved. What I'm saying is that linear dependency between columns will get preserved. Anyway, let's not worry about it. So I hope you understood that if you like, we can also prove it using the using the A, B, C, D, like you using some arbitrary value, but it won't be much useful for gate. So what I'm saying here is that if you do elementary row operations, then you preserve the relationship between columns. There is no change in the relationship between columns. So whatever here it is, it will follow the same, right? And that's where this answer will come in, that how we are making sure using the row operation that we are actually telling the independent columns also. See, suppose you have a matrix which is, let's assume anything, maybe 1, 2, 3, 4, and then 2, 3, anything 8, 12, and now let's have a column which is linearly dependent on these two. Let's suppose this is 3, 5, and 8 and 3 11, and then this is 16. Okay, suppose there is a matrix something like this, and now you perform a Gaussian elimination on this matrix. So suppose that you make all of these as zeros. So what you need to do, maybe you can replace this R2 by by 2R1 minus R2, maybe, right? 2R1 minus R2. And then to make this 0, you can replace R3 also by 3R1 minus R2. Okay, 3R1 will be 6 minus R2. This is 8 minus 2, right? So okay, so let me write R3 minus 3R1, and similarly R4 can be replaced by R4 minus 3R1, right? I mean, you can do whatever you want to do. Ultimately, we want to make them 0. Okay. So let's just try making them 0. It is 1 2 3, 1 2 3, and then it will be 0. So 2R1 minus R2, so it will be 1, 6 minus 5 1, and R3 minus 3R1, so 0, and then this 8 minus 6 is 2, and 11 minus 9 will be 2. Okay, so I think this is 4, not 3, right? This will be 4, and then you will be having this as 0, this will be 6, this will also be 6. Now let's just do one thing. Let's just make all of them also 0, right? By the way, let's suppose I just write till this point. Okay. Oh, okay. Let's suppose I do not write these two numbers. Okay. Suppose, and I just ask you that can you tell me these two numbers? Then I think you should be able to tell me before or without doing all of this row operation. Just these two numbers. If you know that by construction, I'm telling you. Okay. If you know that these two summation give this, right? By construction, like the way I made this matrix is basically these two summation is giving this, which means 3 to 5, like that, right? Now, if I just ask you that what will be these two numbers, then you will say that, see, by construction, like the first column and the second column is giving you the third column. That is why here also, since the elementary row operation does not change the linear dependency between the columns, so here also these two summation and these two summation should give you these two. So which means you will be getting 2 and 6, right? Okay, anyway, like just one point I wanted to say. Now let's just make all of them are also 0. All of them are also 0, right? So what you will be doing, maybe you can do R3 by R3 minus 2R1, 2R2, and R4 should be replaced by R4 minus 6R2, right? And then finally you will be having 1 2 3, 0 1 1, 0 0 0, and 0 0 0. Right? So this is what you will be having here. Now I wanted to actually do all of this exercise just to realize you one thing. See, if you notice that there are only two pivot elements, right? There are only two pivot elements here. And why that is the case? Because there are only two linearly independent columns. So ultimately we have figured it out that the third column is actually dependent on these two columns, and it is actually not having any pivot, right? So the third column is actually a free column, and using the linear elementary row operation, we have figured out that this third column is actually a free column and these two are pivot columns, right? So that's the very powerful technique where I'm actually doing the row operation, but ultimately I'm not just finding out that rows are linearly dependent. See, all 0 rows are linearly dependent. Why? Because see, anyway, this 0 row can be obtained by this row. How? You can multiply by the 0, right? I mean, you know the 0 vector is actually linearly dependent on any other vector. So this 0 is actually linearly dependent on anything else. So that is why, like, I can say that all of the zeros are linearly dependent on all of this, right? And and at the same time, I can say this is independent on this. Why? Because you cannot produce this using this. How? If you try to produce, how you will be producing this 0? You cannot produce 0 from 1. You have to multiply by 0, and the moment you multiply by the 0, everything else will be 0, right? So basically, if it is a non-zero row in the Gaussian animation, finally if you get the non-zero rows, then this is basically linearly independent. 0 rows are linearly dependent. This is one thing. Another thing is that free columns, okay, free columns are linearly independent and pivot columns are linearly independent. Actually, all of this exercise I wanted to do to realize one thing, that if you are doing the row operation, then ultimately you are finding out that this column is linearly dependent on these two columns. How we are finding it out? Let's just check. See, here you have this as pivot, but this column is not having any pivot. Why? Because just think about it. Because these two are pivot. Now suppose this is having a pivot. Okay, suppose this is the pivot. Suppose this is a pivot. Then do you think that our initial thing that we have just seen, that if C3 is equal to C1 plus C2, then this will follow throughout, right? Will this satisfy if this is a pivot? Because these are zeros, right? These are zeros. These zeros, if this is pivot, then these zeros cannot give you the non-zero, right? Because if by chance if this is a pivot, then in that case you cannot satisfy C3 equal to C1 plus C2, and that is followed throughout. That's what we know. So basically what I'm saying is that you have performed the elementary row operation, but ultimately you have found out that the last column is actually linearly dependent column. Although you have performed the elementary row operation, but still you are finding out that last column is linearly dependent column. Why? Because see, the moment you make these as zeros, okay, these as zeros, then automatically the linear dependency, okay, maybe I can give you the simpler example with two vectors only, but for now just try to understand just focus on this thing, okay, just focus on this thing. Now the moment you actually make these two a zero, then automatically these two are automatically becoming zero, right? The moment you make these two a zero, then automatically these two are becoming zero. That's why you cannot have any pivot here. If this column, okay, just assume that you only have this much matrix, okay, this much matrix, and similar like from here you can say that this column is just a linearly dependent on this, because 1 times this 1 into this column will get you this, right? So that is why you can say these two columns are linearly dependent. Now the moment you make them zero, okay, now the corresponding, you make them zero, the corresponding zeros you will be having here also. You cannot have any pivot here. Okay, so let me just do one thing. Let me give you one more example using just two columns. Just assume that these two columns are linearly dependent. Actually you can very much see that these two columns are linearly dependent. Now let's just try doing one thing. Let's just try making these two a zero, and let's just see what is happening with these two. Okay, what is happening with these two? If you are making these two a zero, then let's just observe in the process that what is happening with these two. Let's just see. See, here C2 equal to K C1, right? It should follow throughout. Actually it will follow throughout. Let's just see. Elementary row operations does not change this, so it will follow throughout, right? So let's not worry about it. Now what you need to do, you can multiply this R2. You can say that, okay, maybe there will be some factors. Maybe you can say that R1 can be divided by A1 and multiplied by A2, right? Multiplied by A2 upon A1. So A2 upon A1 will give you A2, right? Cool. And then minus R2, right? If you do that, then you can replace basically the R2 by this. So let's just try doing it. So it will be A1 K1, and then if you do this operation, which is A2 upon A1 into R1, it will make it A2, right? Then A2 minus A2 will be 0. A2 upon A1 into R1, A2 upon A1 will make it Ka2, okay? Will make this number Ka2, and then Ka2 minus Ka2 is actually 0. And then let's apply this also at the same time. Actually by symmetricity you can see that you will be doing the same thing. I mean, instead of A2 you have A3 here, right? Okay, anyway, minus R3. And then if you apply this, then A3 upon A1 you multiply in R1, A3 upon A1. So if you multiply in R1, then you will be getting 0, right? And then similarly you will be getting 0 here. So what is happening? The moment you are making these two as 0, automatically these two are coming to be 0. Why? Because ultimately they have to satisfy C2 equal to KC1. So it should be multiple of that. That is the thing that is getting followed throughout. Maybe I can give you the simpler example instead of A1, A2. Maybe let me try doing a simpler example. Let's suppose you have 1, 2, 3, and then this is 5, 10, and 15. Okay. Suppose this is the matrix that you have. Now you apply R2 should be replaced by R2 minus 2R1 maybe. Okay. And then R3 should be replaced by R3 minus 3R1, right? Now from here you will be getting 1, 5. From here And then if you replace R2 minus 2 R1, then you will be getting 0, 0. R3 minus 3 R1, you will be getting 0, 0, right? So these are the things that you will be getting. Now, now if you observe one thing, that this particular in the what you wanted to do, just let me know what you wanted to do when you were having this in mind. You wanted to make these two as 0, right? Were you having, tell me honestly, were you having anything related to these two should be 0 or something like that in your mind? No, right? I mean, we wanted to make these two 0. But in the process of making these two zeros, you automatically got these two zeros. And that's where the linear dependency are getting captured. So basically, I mean, that's little tricky and you don't need to actually think about it much. But I just wanted to tell you, because of the interviews that you may face this kind of question, like you can explain that the moment you make them 0, the automatically, if this is linearly dependent, this will automatically be 0. Because it has to follow this C2 equal to K C1 throughout. The moment you make them 0, K into C1, automatically 0, right? Automatically 0. So that is why you can say that here you only find one pivot element. Here you cannot, in this column, since it is linearly dependent, you cannot find the pivot element, right? This is a free column. Automatically you will be getting the free column by using the elementary row operations. So that is what I wanted to convey. Okay, so that's where I'm saying wait a minute, which means that you are doing the elementary row operation, but how you are concluding about the columns? Because we are concluding, because like automatically it is getting captured. That's why the Gaussian animation is so powerful, that it is, if it is a linearly dependent column, ultimately it will make sure that you cannot get these as 0, these as non-zero. Because the moment you say that these are 0, see, ultimately, let's suppose you get this as matrix which is row reduced. Okay, row echelon form. Ultimately, let's suppose this is the matrix that is the row echelon form. And in this row echelon form, let's suppose, I mean earlier, let's suppose you knew that this is linearly dependent column. Okay, which is dependent on linearly dependent column, which is dependent on, let's suppose, all of these three columns. This is one column, this is another column, this is another column. So on these three columns, this column is linearly dependent. Suppose, okay. And now you perform the elementary row operation of the Gaussian animation. And now let's suppose that we got some matrix which is something like this. I mean, there will be a pivot element here, right? There will be a pivot element here, and then there will be a pivot element here. And since these are pivot, so this will be 0, this will be 0, 0, this will be 0, 0, 0, right? And let's not worry about like the rest of the elements. It could be anything. So let's not worry about the rest of the elements. Okay. Now, since this column is linearly dependent on these three columns, now what you need to do? You just understand one thing, that since it is linearly dependent, I mean, by construction, the way you have written it earlier, it was like this, and then the row echelon form, it is automatically getting captured. That's my point. Why? See, this is the pivot, this is the pivot, and this is the pivot. Now, the thing is that you cannot have a pivot here because the corresponding are 0. And since it is linearly dependent, then there must be some relation earlier. The C4 must be C1 plus C2 plus C3 or some relation, right? Then if it is non-zero, then will this relation will get followed here? No, right? You cannot get non-zero out of these three zeros. So if these are zeros, then automatically this is 0. And that's why this column becomes a free column. That's my point. Okay, so this is actually just optional video. I mean, you do not need to know all of this. I just told you, maybe in the interview they may ask you, like maybe, that's also maybe. Okay, so I hope you liked it. If you do not understand, if you have not understand something here, if you have not understand anything, then you can just rewatch it, but let's not worry about it. Okay, because for GATE perspective, it might not be required. Okay, so thank you so much. In GATE, actually, they have not asked anything. They won't ask. I mean, they cannot. I don't think there can be a question on top of this intuition. But in the interview, they may ask you something like this, right? So that's why I have just explained you, so that we are completely prepared for everything. Okay, thank you so much.